Okay, so this is quiz number 2. This is my second attempt. On the first problem, I think I just made a calculator error down here at the very end of the problem. So this is pretty similar, it's just with the different numbers. And so for quiz number 2, I'll just go over my work again. We're told that a car stops on a flat road, and we're given the distance that it takes for it to stop, and then we're told to find the distance that the car can stop if it's on an incline going up the hill. And so to start off with, I just looked at the things that we were given in the problem. So we were told the initial velocity of the car and the final position on a flat road. We can also assume from the problem that the final velocity will be 0 because the car is stopped, and I set my initial position to 0. And so right here I drew a free body diagram and set that equal to my kinetic diagram. So basically we have the normal force going up, we have our weight of the car going down, and then the force of friction from the tires pulling the car back. And so the problem told us to solve this using our kinetics problems, force equals mass times acceleration. And so I used an XY coordinate. I set my direction here. And so the forces in the Y direction, the only forces we have are the normal force and the weight. And we know that the acceleration in the Y direction is 0 because the car is not moving in that direction. And so solving that, we can find out that the normal force of the car equals mg on the road. And then in the x direction, we have the force of friction, and that has to equal the mass times the acceleration in the x direction. And we know that the force of friction is mu times our normal force. And so looking at this, we know that our normal force is mg from our first equation here. So we can replace that with our normal force, and we can find out. So basically what we're trying to do here is solve for our coefficient of friction, mu k. So we can use that on the other ramp. And so basically we have this equation, but we still need the acceleration in the x direction. And so what I did was use our equations for constant acceleration. This is the equation here that I used. And we plug in what we know about this problem, and we can find our acceleration, or I should say deceleration, in the x direction. And then using that, we can plug that in here. Our masses will cancel, and we can find our coefficient of friction for kinetic friction, and that's what this is here. And then once we have that, we can move on to the second part of this problem. And so I redrew our car here, and he's going up this incline at 7.7 degrees. And we want to know how far it takes him before he stops. And so this is my second free body diagram here. This time our normal force is perpendicular, and I tilted our axis here to make the problem a little bit easier, and that equals mass times acceleration, stopping the car. And so similar to on flat ground, I created a force equals mass times acceleration equation in the x direction and the y direction. And looking at those, we had some information that we could plug in to simplify those equations. And so in the x direction we had the force of friction, and then we had mass times gravity times the sine of that angle, or our weight pulling the car down basically, and that equals mass times acceleration in the x direction. And so plugging in force of friction we know is mu times our normal force. And then we can replace our normal force with what we get from y. And so looking in the y direction, similar to over here, we can find what our normal force is, and it's mg times cosine of our given angle, 7.7 degrees. And so replacing our force of friction with mu and our normal force gives us this equation here. And then that equals mass times acceleration. And then looking at this, we know that our masses will cancel. And we can plug in what we have here to find our acceleration in the x direction. And so once we have our acceleration in the x direction, we can go back to that same equation where v final squared plus v initial squared equals 2 times acceleration times our change in position. And so since we're starting in a position of 0, we're looking for that final position. And so taking the acceleration that we found using our coefficient of friction, we can plug in those numbers and solve for our position, which turns out to 36.2 meters. And so that is the answer for this problem.